we talked about PI control and PD control at the motor level. But let's talk about what happens at the robot level. So in this particular case, the end effector of the robot is right here. And let's say I want the end effector to move to a new position. Right? Let's say somewhere over here. Then there are a couple of different things that are going on when I'm asking the robot to do that. First, there is a high level control that sits in a box like this over here that calculates for the end effector to move there, what do all the different motors need to do. Now let's see if the robot can execute a motion like that. And watch carefully, while the end effector is moving there, the motors are all doing different things. Did you catch that? You might want to rewind and see what each of the 6 motors were doing. And once the motors know what they are supposed to do, there's a lower level control which implements PI or PD control depending on which mode it is in. That is just worrying about whether the motor is rotating the right amount or not, and each one of them have their own independent lower level controller that implements that. And typically in a setup like this, the motors along with the lower level controller is sitting at each of the joints. And this together has the 2 level higher level control and the inner level or inner loop control. And as we discussed, the inner loop control typically operates at a much higher sampling frequency or sampling rate than the higher loop control. Now this is how both of those work together to make this motion happen.
We just saw on the robot why we need rotation matrices and homogeneous transformations. Now let's get to the theory. What is a rotation matrix? It's nothing but a mathematical relationship in matrix form, obviously, of the relationship between 2 coordinate frames with different orientations. So here I've shown one coordinate frame which is the blue frame, let's call it the 0 frame, x0, y0, z0, and another coordinate frame, the 1 frame which is x1, y1 and z1. And for the moment we are not worried about the origins being different, we are just worried about the orientations. So we will assume both of them have the same origin. So what we are trying to figure out here is, supposing there is a point here in 3D space, let's call it P, and there is this vector P. Now this vector P can be expressed in terms of the components along x0, y0 and z0, and it can also be expressed in terms of components along x1, y1 and z1. What would that relationship be? The components along one of the coordinate frames versus components along the other coordinate frame. That is what we are really trying to establish here. Okay, so let's consider vector P, and let's say P0 is nothing but vector P expressed in terms of components along x0, y0, z0, and similarly P1 is the same vector but with components expressed along the other coordinate frame. So vector P expressed in terms of components along x1, y1, z1. So we can now go ahead and write P0 as P0x along I0 hat or I0 hat, P0y along J0 hat, and P0z along K0 hat, and P1 as P1x I1 hat plus P1y J1 hat plus P1z K1 hat. And we are trying to figure out a relationship between the components over here and the components over here. So we start with taking advantage of the fact that these, so P, P0, P1 are all the same vector essentially, they are all equal. And if I were to write an expression for P0x, can you figure out what that expression would be? It is simply P0 dot with I0 hat. This is obvious, but it's also a little weird because to find P0x along I0 hat, you have to take P0 and dot it with I0, and it works out if you see it. So now, taking advantage of the fact that P1 and P0 are the same, I can also write this as P1 dot with I0 hat. And now I can plug in P1, the expression for P1 over here, and I would get P1x I1 hat dot with I0 hat plus P1y J1 dot with I0 hat plus P1z K1 hat dot with I0 hat. It is starting to look a little bit complicated, but it is really not. All we did was express the first component of P along the x0, y0, z0 frame in terms of a dot product and simply plugged in expression for P1 over here. Now I can go ahead and do the same thing for P0y, and I would get P1x I1 but now dot with J0 hat, and P1y J1 dot with J0 hat, and P1z K1 dot with J0 hat. And similarly, I can do the same thing for the third component P0z, and just to reiterate, P0z is nothing but P0 dot with K0, and P0 is the same as P1, so I can write it as P1 dot with K0, and for P1 I can substitute this entire expression, and again I get this P1x I1 dot with K0 plus P1y J1 dot with K0 or K0 hat, and P1z K1 hat dot with K0 hat. Okay, so now that we have these three equations, we can write them in more compact form, and they would become P0x, P0y, P0z is equal to a matrix multiplied by P1x, P1y, P1z. And looking at this pattern here, I would simply get a bunch of these dot products here in the matrix. So I would get an I1 dot with I0 hat here, I would get a J1 dot with I0 hat, and I would get a K1 dot with I0 hat. And in the second row, I would get I1 dot with J0 hat, J1 dot with J0 hat, and K1 dot with J0 hat. And finally, in the third row, I would get again I1 dot with K0 hat now, J1 dot with K0 hat, and K1 dot with K0 hat. Okay, now that we have done the hard work, this is the most complicated part of writing these matrix relationships. From this point on, it only gets easier. But now that we've done the hard work, now let's look at this matrix and see what this is really doing. This matrix relating components of vector P along x1, y1, z1 to components of the same vector along x0, y0 and z0. So this matrix is called a rotation matrix going from frame 0 to frame 1. So I'm calling it R, standing for rotation matrix going from frame 0 to frame 1. And if I take the components of P in the one frame and then pre-multiply it with this matrix, I will get the components, sorry I missed it, components of P in the 0 frame. Okay. Now this is an interesting matrix and has a bunch of interesting properties. One, these are both always the same vectors, right? Physically it's the same vector, it has the same magnitude and same direction, which means no matter how much the rotation is between these two frames, the magnitude of this vector, the P1 vector and P0 vector, would have to be exactly the same. That would automatically mean that our matrix cannot scale up a vector or scale down a vector. Do you know what that translates to in terms of mathematical properties? It means that R would have to have determinant 1. Do you agree? Do you think that's what it is? Okay, go back and look at determinants and see if that gives you that property. If R always has determinant 1, would that mean that there is no scaling between these two vectors? Okay, so that's one. Second, obviously all of these entries are now dot products between unit vectors only. So a dot product between two unit vectors can never be more than 1, right? So all of these entries would be entries less than 1, right? Or rather between +1 and -1. These are also probably something very familiar to you. You might have seen in mathematics in, maybe some of your earlier courses. These are nothing but direction cosines, right? It's just an arrangement of direction cosines. Now this also has an interesting name. So this R is said to be a vector in SO3. SO3 standing for special orthogonal group of order 3. Now what is this thing about orthogonal group? So we'll come to that in a second. So let's save this. This another interesting aspect here, which makes this an orthogonal matrix. Okay. Now if instead of first writing components of P along the 0 frame, if I had done the reverse, right? So if we do the reverse, meaning what? If I had written P1x, P1y, P1z, and if I had gone through exactly the same set of steps. So P1x means P1 dot with I1, and since P1 and P0 are the same, I would then write that as P0 dot with I1, and for P0 I would have plugged in this whole expression, and if I go through that and do the same thing for all three and then write it in matrix form, and you can do that, it's relatively straightforward, then can any of you figure out, without going through the entire math, how different would that matrix be as compared to this matrix? And of course this would have a different name because this is now P1 on the left hand side. So this would still be a rotation matrix, but this would be a rotation matrix that is going from frame 1 to frame 0. Now the question is, how different would R1 to 0 be from R0 to 1? Have you figured it out? It turns out you will have all these same dot products but arranged in a different way, right? So this would be nothing but simply the transpose of this matrix, right? So once you work it out, you will see R1 to 0 is R0 to 1 transpose. But you guys know how to work with matrices. When you have a vector is equal to a matrix times another vector, if you wanted the reverse relationship, you could take the inverse of this matrix and pre-multiply on both sides. So then you would get an expression similar to this. So it turns out this is also the same as R0 to 1 inverse. So this is an interesting property of these matrices. The inverse of a rotation matrix is nothing but the transpose of the matrix. This makes life a lot easier. You know, computing inverses are hard, but computing transposes are easy. I would always, I would any day take this situation where if to compute an inverse, I just have to compute a transpose. So that's why these are called orthogonal matrices, because the inverse of the matrix is the transpose, and this is true for all rotation matrices. This is just an example that we did, but this is a general enough derivation that this is applicable to all rotation matrices. They always have determinant 1, they are always orthogonal, and they are said to be in SO3. They never change the magnitude of the vector. And it's just a matrix multiplication to transform from coordinates in one frame to the other frame. Now we can use this a little bit, in more complex situations where we are not just talking about 2 frames, but we are talking about a sequence of rotations. And as we saw in the robot, there are a number of joints, each one could be rotating a different amount, and you want to be able to do these calculations repeatedly over and over again. So now let's look at a different situation where you still have this, but you have another rotation sequentially after this. So we just saw that P0 is R0 to 1 times P1, and it turns out R1 to 0, which is the reverse of this, is nothing but R0 to 1 transpose, which is also the same as R0 to 1 inverse. But now we can talk about also having another transformation from P1 or 1 frame to 2 frame. Let's imagine a sequence of 2 rotations. So R1 to 2, P2. P2 is still the same vector, but expressed in terms of another coordinate frame with different orientation. Now it is obvious that if I wanted to look at the relationship between components along 0 frame and components along 2 frame, still the same vector, right? I can work out that relationship by simply plugging in this expression for P1 over here, and I would get P0 is equal to R0 to 1, and instead of P1 here, I plug in the whole thing here, which is R1 to 2, P2, and that tells us that multiplying these 2 rotation matrices together gives me the relationship between the 0 frame and the 2 frame. So this is again a nice property of rotation matrices. When you have multiple rotations involved, you simply have to figure out the individual rotations and multiply them together. But one thing to be careful here is this is a matrix multiplication. So if you reverse the order, the result changes. And it has to be in a specific order. So you remember this order, and that's something that can be very confusing. Setting up rotation matrices, remembering the sequence of rotations is something that remains confusing for a long time. Every time you set up a new robot, you will again feel like you are a little bit confused with this, but don't worry, you will be able to figure it out. Okay, so we were able to do multiple rotations as multiplication of rotation matrices. Now the task is, every time do we have to figure out all the unit vectors and dot products of all the unit vectors? The answer is no. We will use this fact that we can do multiple rotations and then multiply them together. So every general rotation, we will think of it as a sequence of simpler rotations. That makes this life a lot easier for us. So let's think of some standard rotations. So if it so happens that I have my blue frame as the 0 frame, and my red frame happens to be just one rotation about the z axis by angle theta, which would mean that my z axis is still along the same direction. So my z0 and z1 are collinear, but I would get my x1 and y1 to be rotated, but still in the same xy plane. So if I go ahead and write down x0, y0, z0, it would mean that this angle is theta, this angle is theta. They are still all in the same xy plane, and z1 is still along the same direction as z0, and this would be y1. Now in this case, you can go back and look at the rotation matrix expression, and you can figure out all these dot products, but some of the things would be obvious. So k0 hat and k1 hat dot product would be 1 because they are collinear, right? So some of the, and then all the k's will be perpendicular to all the i's and j's, so those terms will be 0. So you can go ahead and have a much simpler expression for this rotation matrix. So this is called R about z by angle theta, because this is a standard rotation about axis z by angle theta, and this would end up, you can work out the direction cosines. They are straightforward. You would get cosine theta minus sine theta 0, sine theta cosine theta 0, 0, 0, 1. This is how the rotation matrix will look like. So it's called standard rotation or basic rotation about z-axis. This makes life a lot easier because every time we are not working out the dot products. The minute we see there's a rotation about z-axis, we can blindly apply this expression. And as you would have guessed, you would have two more basic rotation matrices. You have basic rotation about y-axis by angle theta and basic rotation about x-axis by angle theta, and this would be cosine theta 0, sine theta 0, 1, 0, minus sine theta 0, cosine theta. And last one is basic rotation matrix about x-axis by angle theta, and this would be 1, 0, 0, 0, cosine theta minus sine theta 0, sine theta cosine theta. Now the good news is these are all the rotation matrices that you would ever need. Why? Because any three-dimensional rotation, you can always think of that as a composition of a sequence of rotations about x, y, and z axis. So you can think of a rotation like this as first you rotated a certain amount about the z axis, then you rotated a certain amount about the x axis, and so on and so forth until you reach the new configuration. Remember, the sequence of rotations is important. The other thing that can be very confusing, but let me reiterate again, is P0 is R0 to 1 P1, right? So if I take this example, I start with the blue axis, then rotate by angle theta, and I get the red axis, which is the 1 axis. So I think of starting with blue, then rotating, and I get this rotation matrix. But then this rotation matrix I have to multiply with the new coordinate, or coordinate in terms of the new axis, to get back the coordinate in terms of the old axis, the blue axis. So this is again, this sequence is something that can be confusing, so I'm just going over it one more time. The way you figure out this rotation matrix is you start with the original or the 0 axis, you figure out what rotation needed to be carried out to reach the configuration of the 1 axis. and if it's a basic rotation, you basically pick up one of these. But then the way to use it is you are always using coordinates in the one frame first, then multiplying it with the rotation matrix, pre-multiplying to get the coordinates from the 0 frame. Right? So remember this sequence. You figure this out by going from 0 to 1, then you take the 1, multiply it with this matrix to get back the 0. Right? So your computation is always kind of going back and forth. So this completes rotation matrices. You just have to remember these 3 basic rotation matrices, and then remember to imagine any arbitrary rotation as a sequence of simpler rotations, and just keep multiplying these matrices in the right order to get the relationship between the vectors.